Hi class, in this recording we're going to focus on sight and sight. And before we can really dive into sight, we need to talk about what light is and how the nature of light influences how we perceive light. So let's talk about what sight is. Sight can be defined as our perception of objects um, by means of the light they reflect or omit, depending on whether it's glowing, if it's a light source, or if it's a piece of black body that's not giving off light directly. So as we look at light, what we define as light is the visible part of the electromagnetic spectrum. When we think of light, most people don't like to think of it as radiation, but visible light is a form of radiation. Visible light for human beings is going to range from 400 nanometers to 700 nanometers, with 400 being the blue and 700 being the red ends of the spectrum. As we look at these different wavelengths of light and the wavelengths in between, so 450, 600, 537 nanometers, all these different wavelengths in between, they all can cause photochemical reactions where the photon of light will hit a molecule, cause the molecule to change shape, and as we change shape, as we change the structure, we change the function and can initiate a cascade of chemical reactions, which ultimately becomes an action potential or nerve signal, which we process as light. Anything that has a wavelength less than 400 nanometers is going to be referred to as ultraviolet radiation and will have too much energy and so much energy actually that it destroys the macromolecules, the large molecules that we use to process photons of light. So this can be kind of counterintuitive, but the smaller the wavelength, the higher the energy. Now, on the other end of the spectrum, greater than 700 nanometers, we refer to as infrared radiation. It doesn't have enough energy to cause the photochemical reaction, but it does have enough energy to cause warming of tissues. So when we think of infrared radiation, I remember the example my physics prof gave years ago. When you're getting a hug from somebody, that warm feeling you get from the hug, a lot of that warm feeling is infrared radiation from the person who's hugging you being transmitted to your body. Now, as we look at our eyes, we have some optical components of our eyes that we use to get the light to the macromolecules we use to initiate our photochemical reaction. We have a membrane on the outside, on the far anterior of our eye, that's referred to as the cornea. And this cornea is a very tough, very fibrous layer. If you ever have had the pleasure of working through a brain dissection, you know exactly, or excuse me, an eyeball dissection, you know exactly what I'm talking about. As we look at the cornea, our cornea has a lot of aqueous humor moving around within it. That aqueous humor is going to be generated near the ciliary body. It'll flow over the front of the lens, through the pupil, and then move within the chamber referred to as the anterior chamber made by the cornea over the pupil. And this aqueous humor is going to eventually be absorbed by the scleral venous sinus, located at the edge of the cornea, around the circumference of the cornea. And an important thing is that we absorb aqueous humor at the same rate that we generate aqueous humor. Now, as we look at this word, aqueous humor, this first term, aqueous, refers to watery, which means it's a very thin liquid. The technical term for this is serous. Humor is a really old school term, and in this context, we don't mean funny, we mean liquid. Humor is an old word that refers to a liquid. So the aqueous humor is the serous fluid, or the serous liquid that's being circulated through the anterior chamber of our eye. Oh, there we go. Now, as we look at the lens of our eye, which is right here, is going to be made of fibers. And these fibers are actually individual transparent cells. So if you have a chance to do an eyeball dissection, take the lens out. It looks like a little oblong marble, and let the lens dry out on your lab station overnight. And then the next morning, you can see the individual lens cells that have pulled apart from each other as they have desiccated overnight. To hold these lens cells in place, we have suspensory ligaments. I'm using yellow right now to highlight the suspensory ligaments. Those suspensory ligaments are going to be attached to the ciliary body. And I'm going to go ahead and use green for our ciliary body. And that muscles of the ciliary body will apply pressure to the suspensory ligaments. The suspensory ligaments transmit that pressure to the lens, and ultimately that's going to cause the lens to get tugged and pulled on, so the lens will change shape. And as the lens changes shape, it's going to impact how light is focused. So as we look at our lens, the default shape of our lens is to be rounded if we don't have any tension. So if we're going to be lazy and just let our eyes relax, our lens becomes very round. And if we're trying hard to focus on something, well then contract the muscles of the ciliary body and then pull on the lens to flatten the lens. And by flattening the lens, we change how light is processed by it. As we're looking at our posterior chamber, our vitreous body, and this is a mistake right here, the posterior chamber in this figure, the posterior chamber is posterior to the lens. The vitreous body, also known as the vitreous humor, it's a jelly-like liquid that fills the posterior segment. And this vitreous humor it has the consistency almost of mucus, for lack of a better term, or partially congealed jello. And as we're looking at this vitreous humor and the aqueous humor and the two chambers of the eye, plus the lens and the cornea, light travels through all of them. So I'm going to use a black line here. Light will go through the cornea, through the aqueous humor, through the lens, and then through, looks like I'm running out of room to draw, I'll go off to the side here, and then through the vitreous humor, as it's working its way back to the retina in the back of the eye. Now, once we get the light to the retina, we're going to shift from optical components to neural components, because we need to start focusing on taking a photon of light and turning it into an action potential. Ultimately, when we look at the neuronal components, we're referring to the retina and the optic nerve. The retina itself is a membrane that's on the posterior of the posterior chamber of the eye. So it's on the back of the inside of our eyeball, to use common speak. And as we're looking at it, it's going to be attached to the eye only at the optic disc. Our optic disc is located right here. And you can always find the optic disc in a diagram or figure, because that's where all the blood vessels converge at. The optic disc in a dissection is quite easy to find, because the optic disc is directly opposite to the optic nerve, cranial nerve number 2. And to help hold our retina in place, we have the vitreous humor, that jelly-like fluid in the posterior chamber, pushing the retina back and holding it in position. Occasionally, our retina can detach, and if our retina detaches, we can have blurry vision that ultimately leads to blindness. As we look at the retina, there's a patch of cells in the retina directly in the center. So I need to emphasize right here in red, I just circled the dead center of the retina. The optic disc, where the retina attaches, is not the center of the retina. And that's a good thing, because the optic disc represents a blind spot for us. The macula lutea is in the center of our eye. And this is a patch of cells that is where we focus light. And then in the very, very center of the macula lutea, there's a small indentation. I'm going to use a blue dot for that. That blue dot represents the fovea centralis. And this macula lutea and fovea centralis are both where we have the majority of our color processing. Most of our highlight or color processing cells on our retina are going to be located within these two structures. As we look at the optic disc, our optic disc is referred to as a blind spot, and it's a blind spot because of all the blood vessels that are on the surface of the retina converging at the optic disc. It's also going to be directly opposite to the optic nerve. I have on the top of the screen a blind spot detection apparatus, and it's just a simple idea that you can look at one thing and then the other thing will disappear as you're staring at the object you're told to stare at. So I just did it right now, super quick. Of course you can't see because this is a recording of my screen. But what I was doing was I closed my right eyeball. I was staring at the X with my left eyeball. And right now I'm sitting at a desk in front of a laptop computer. And I just wobbled my head back and forth while I was looking at the black X with only my left eyeball. And when my eye was about 18 inches, or we'll say 18 to 24 inches away from the computer screen, this red dot disappears from my field of vision. Now, as we're looking at the filling of our brain, visual filling of our brain, if I stare at this black X with two eyes open, the red dot never disappears because our two blind spots don't overlap with each other. Also, we should focus on the fact that this blind spot is filled in with green. So when something gets into our blind spot, our brain will automatically make a best guess and say, well, if there's a green bar here, a green bar here, there's probably going to be a green bar right in the middle, and I'll just go ahead and fill that in with a green bar, even though there's a red dot right there. That's all we have for this recording. If you have any questions or comments about how the optical or neuronal parts of the eye, please feel free to post them on the class discussion boards or to shoot me an email. And as always, happy studies.